Welcome! The webinar you are about to view presents a derivation of Maxwell's equations from a simple two-component solid ether. I am Dr. Delbert Larson, and the work you are about to view was predominantly worked on in the early 1990s during the closing days of the superconducting supercollider. My work was eventually published in the reviewed journal Physics Essays in 1998, and a copy of that publication appears on this website. As is common in published works, the paper itself is quite short and many intermediate steps in the derivation are skipped over. The paper also introduces some new terminology. As a result of these issues, the paper can be quite difficult for a student to follow. The purpose of this webinar is to achieve a presentation that is easier to understand. For one improvement, I wish to thank George Galecki, who during one of my few presentations suggested that I call the two ether components positive and negative charge. While it is not quite accurate to call them charge, I have renamed the components negative and positive ether in the presentation here. I have also made an effort here to draw diagrams to support the mathematics wherever possible, and I have put in all the intermediate mathematical steps of the analysis so that it is far easier to follow than is the original paper. Of course, Maxwell's equations are relationships that involve vector calculus, and for this reason I also include a brief review of vector calculus in this presentation. This webinar will present a derivation of Maxwell's equations from a simple two-component solid ether. Presently, the concept of an ether is considered by the majority of physicists to be an old, discredited idea. But if we dig past the superficial politics, it can be seen that an ether concept has many intuitive advantages. The classical physicists believed that an understanding of nature should enable physical laws to be stated in words as well as mathematics, and that an underlying physical model for the mathematics was crucial to that understanding. Waves were believed to be the result of a substance in motion. In the case of light, this required the existence of a new substance, the ether. Maxwell devoted a considerable amount of his life toward the pursuit of a mechanical model that would underlie his famous equations. Today, however, proposing a classical ether leads to a confrontation with special relativity. It is well appreciated, even celebrated, that relativity correctly predicts experimental results. What is less appreciated is that the precursor of relativity, Lorentz's theory of electrons, equally well predicts the results of experiments. It is generally taught that Einstein greatly simplified the idea of space by abandoning the ether. But what is not emphasized is that special relativity replaces the simple ether concept by a triply infinite set of equivalent spaces and times throughout the universe. By reintroducing an ether, we regain the simplicity of a single space and time. Whether Einstein or Lorentz is correct is still an open question. No experiment has ever been conducted that would indicate that Lorentz was wrong. In fact, Bell's theorem tests provide some evidence that supports Lorentz's view over Einstein's, and that topic is discussed more fully under the Space and Time tab on this website. The approach taken in this webinar is to assume that Lorentz is correct and that an ether does exist. Under that assumption, this webinar will now present a mechanical model that will be shown to lead to a derivation of Maxwell's equations. An approach to science that I especially like is to start with a set of axioms and then go on to see if those axioms are a good representative of nature by developing those axioms into testable hypotheses. While it is a plus for those axioms to seem reasonable, it should be remarked that science does advance with axioms that initially seem radical, so I believe we should reserve judgment on any theory until the tests of it are made. The axioms of the model proposed here are as follows. Newton's law will be assumed to be correct in the form F equals dp dt, where F is the force, P is the momentum, and T is the time. The usual definitions are assumed, where the momentum is beta gamma mc, where gamma is the square root of 1 over 1 minus beta squared, beta is v over c, v is the distance traveled per unit time, or the velocity, and c is the speed of light. It is also assumed that in the absence of sources and waves, a homogeneous, isotropic, two-component, solid, incompressible ether occupies all of space. From the fact that electrostatics and the theory of atomic dislocations in a uniform solid-state lattice are both governed by Poisson's equation, it follows that the scalar potential may result from the dislocation of one thing with respect to another. Hence, it is here postulated that the ether is made up of two components. One component will be called the positive ether, and the other will be called the negative ether. The axioms on this screen are among the most likely axioms one could imagine, and only the two-component nature of the ether might be considered a new idea. But even there, most material we run across in our day-to-day lives also consists of positive nuclei and negative electrons, so even the last axiom can be regarded as an entirely natural assumption. Moving on from the initial assumptions, it will be proposed that in the absence of sources and sinks, each small volume of negative ether is attached to an equally small volume of positive ether. However, it will be assumed that it is possible for this attachment to be broken, resulting in free, detached ether. Drawing from the standard theory of dislocations within a solid, the presence of a source is evidence of some extra substance disturbing the otherwise homogeneous material. Sources are therefore proposed to be regions wherein there is some extra positive ether. For the model proposed here, this extra ether is postulated to no longer be attached to the solid. It is detached and free to move about within the remaining ether. Since the source and sink term in Maxwell's use of the Poisson's equation is identified as electric charge, detached positive ether can now be identified as positive electric charge, while detached negative ether can be identified as negative electric charge. This model then readily leads to an understanding of the law of electric charge conservation. Whenever a given volume of positive ether becomes detached and positive charge is formed, an equal amount of negative ether becomes detached, and an equal amount of negative charge is formed. At this point, it is good to try and picture what the ether consists of. Here we see a cube of ether, as well as a free piece of positive ether, and a free piece of negative ether. The ether can be envisioned as a typical ionic solid, although in the case of the ether, positive ether plays the role of a typical positive ion, whereas negative ether plays the role of a typical negative ion. Free detached ether occurs when some of the bound ether becomes detached from the lattice of the solid. Note that this model has two relevant precursors in the history of science. In 1930, Paul Dirac postulated a theoretical model of the vacuum as an infinite sea of particles possessing negative energy in order to explain the anomalous negative energy quantum states predicted by his equation for the relativistic electrons. In the ether model proposed here, it is seen that there are two such infinite seas, one positive and one negative, and that they are bound together in a solid lattice. The second precursor comes from standard solid-state physics of semiconductors. In typical silicon bonding, each silicon atom has 4 valence electrons that contribute to the bonding within the lattice. By introducing dopants with 5 valence electrons, an extra electron is brought into the lattice structure. This extra electron is free to move within the lattice, which is what leads to the conductive nature of the semiconductor. Similarly, it is proposed here that the detached ether components are also allowed to flow within the lattice. The extra components can flow since the bound components already have a partner with which to bind, allowing the extra component to flow throughout the solid, similar to the electron flow in the N-type semiconductors. Since we have postulated that the ether is incompressible, note that when a positive portion of free ether enters the cube, the other positive portions must bulge outward to make room for it. As we will see later, an analysis of these and other displacements will lead to a derivation of Maxwell's equations. We are now ready to consider possible force laws required to analyze ethereal motions. From Maxwell's equations, it is known that a current, which is flowing charge, acts as a source term. Therefore, flows of detached ether should lead to forces. For the remainder of this work, the following simple force law is postulated. Here is the flow force law. When ether moves with respect to attached ether of like kind, a force is generated on the attached ether that is proportional to the rate of ether flow, and the direction of the force is in the same direction as the flow. When ether moves with respect to attached ether of the opposite kind, a force is generated on the attached ether that is proportional to the rate of ether flow, and the direction of the force is in the opposite direction as the flow. Note that since the force generated by a moving charge, detached positive ether, on the attached negative ether is in the opposite direction as the force generated on the attached positive ether, the net reaction force back on the charged particle is zero, and there is therefore no drag force felt by moving charges as they move through the ether. Since all matter is composed of elementary particles, this overcomes one of the classical problems of the ether, which is how planets and stars could move through an ether without slowing down. Since elementary charged particles can traverse the ether without energy loss, so will larger bodies that are, after all, made up of those elementary particles. We know from experimental evidence that light exhibits transverse polarization. Further, we know that waves in a solid are observed to exhibit transverse polarization, whereas waves in a fluid are not. This fact about ordinary materials leads itself to the conclusion that the ether must be a solid. Waves on a solid string exhibit many of the properties of light. Waves on a string exhibit transverse polarization. The underlying medium, the string, is a solid under tension. For this reason, the two ethereal components assumed herein are each proposed to be a solid under tension. The tension is herein postulated to obey the following simple force law. The tension force law is that when a small cube of ether is deformed, the magnitude of the tension perpendicular to each of any two originally parallel faces is proportional to the separation of those two faces. Tension is equal to some constant, k sub 1, times L. Note that the tension force law, like the flow force law, is about the simplest law that we could postulate, and that the numerous examples of such forces exist in nature. And now, with the axioms of a two-component solid incompressible ether and our tension and force laws all in place, we are ready to see if this set of axioms and laws leads to the known experimental results by attempting to derive Maxwell's equations from these starting points.